Okay, let's get started. So today is my great pleasure to introduce my colleague, Professor Will Scheideler, for this joint seminar talk. So Will joined us back in 2019. He got a bachelor degree from Duke. It's the highest honor, right? And then he got NSF fellowship to do a PhD in UC Berkeley, and then moved to Stanford for postdoc. And he's mostly working on this additive manufacturing of electronics and optoelectronics materials and devices, as you can see from the title. And this is really from the nanostructure all the way to high throughput printing on a microscopic scale. Since he joined in 2019, I would say Will's career really flourished. He actually received this outstanding Young Manufacturing Engineering Award back in 2023 from the Society of Manufacturing Engineers. And the same year, he also received Dartmouth's Woodhouse Teaching Award. So basically, he's a great teacher, as many of the students know. So looking forward to your talk, Will. Yeah.
All right. Thank you for a really kind introduction, Jifeng, and great to see all of you. It's a pleasure to be able to share some of the research that we're doing in my group. So I'm going to be discussing nanomanufacturing for flexible electronics and energy devices, and I've chosen a cross-section of our work that hopefully will cover a pretty significant fraction of all the students that have contributed to this work. So many of you are here in the room. Thank you for coming out. For those of you who might be on Zoom, thank you to the alumni from our group as well. And I just want to start by acknowledging all the hard work that you've put in and some of the good times that we've had. So I've chosen a couple of vignettes, to use Colin's word from his seminar a couple of weeks ago, that will cover electronics and energy and hopefully a broader scope of topics that would fit the rest of Thayer. This sort of themes that underlie a lot of the work that we do are the intersection between materials and device physics and scalable manufacturing. And so we think about devices like thin film transistors and solar cells and various sensors. We think about how to develop manufacturing methods that can make two-dimensional materials, that can make three-dimensional devices, and variations of those in between. So I'm going to cover essentially 3 of the 4 topics. And if anyone wants to see more after hearing me for an hour, I know that might not be the case, but if you wanted to hear more, we will have a public webinar as part of our Dartmouth PMIC Center coming up in a couple of weeks. Oh, at the top? Okay. Is the mics on? Okay. Thanks, Ashley. All right, perfect. So I was saying, if you wanted to hear me talk for more than an hour, I have another seminar on March 5th as part of the Dartmouth's PMIC Center. I also have a webinar for the Electron Device Society coming up here in about a month. So a couple of opportunities to discuss some of the research that I won't have a chance to cover today. The materials that sort of describe a lot of the work that we do are liquid metals and their oxides. So I'm going to be covering essentially our use of liquid metals as a synthetic platform. I won't have a chance to discuss some of our work in stretchable electronics that my student Cypher has been leading, but at these other talks, I will in the future. So I want to start by motivating some of the work and sort of giving our perspective and how we think about semiconductor technologies. If you think about semiconductors as a whole, there's a lot more beyond computing and microelectronics, and I want to specifically point out applications to energy and power technologies, because semiconductors and the materials and the fabrication technologies all underlie advances in those areas as well. If you think about computing, it's really been advanced by increasing integration densities. So billions of devices, or even Applied Materials and other companies now are saying 1 trillion devices on a single die. That's allowed us to be really energy efficient, to communicate with really high bandwidths. But some of the other really interesting advances today that are enabled by Moore's Law and all of the other technological developments in the semiconductor industry are essentially going to larger areas as well. So if we think about information display, sensing, wearable devices, the advances and the interesting things happening in those spaces are taking place on larger areas. So it's a different set of problems than you have traditionally in microfabrication and microelectronics. Now, all of those investments the semiconductor industry has made before have brought us to this point. And if we look out into the future, the things that we're being told essentially are that the future looks like billions or trillions more devices. We're going to have essentially many, many more chips that drive artificial intelligence, drive all of these other emerging trends. The trade-offs, though, we're going to have greater energy efficiency per functionality. We're going to have essentially greater computing power. But the trade-off is that we're also going to have more energy-intensive manufacturing. Semiconductor manufacturing has gotten really complex, hundreds or thousands of steps that a single wafer goes through. So the burden, the externalities from that, that we have to deal with the waste, the toxic waste in many cases, alkylfluorinated substances, additional water use, and a lot of scarce resources and metals that are involved. So those are some of the challenges we have to overcome. The other major trend in microelectronics that I want to highlight is that things are becoming more diverse outside of simply computing technologies. So instead of just moving data around and computing with that data, we're also developing technologies that allow us to interact with the physical world. And that describes a lot of the different materials and devices that I'll be presenting today. So our ability to essentially sense and communicate and actuate and develop technologies that are that interface to the world. It could take place in the Internet of Things as we sort of distribute our microelectronics around different surfaces in the world, develops autonomous technologies like autonomous vehicles, and then also how we perceive the world in augmented reality or virtual reality. And the message really that I want to start with is that silicon microelectronics is really good at all of those things that I mentioned before. It's not as good when it comes to that physical interface to the world. We package silicon up, we put it in packaging to essentially insulate it from the rest of those effects. But if we want to actually interact with the world, we need other materials that allow us to do that. Flexible and printed electronics is the focus of our research group. And the reasons that we're interested in that, for example, are that printed and flexible electronics can be conformal. We can put it in the body or on the body in places that we can never put microelectronics previously. We can integrate multifunctional devices, so a lot of different sensing capabilities or actuation in the same system. That's challenging or prohibitively expensive to do with a lot of traditional microfabrication technologies. We also have the ability in large area systems like arrays of thin film transistors to have some spatial perception. That our skin, for example, right, we know not just the magnitude of a force, but we know where it's being applied. Thin film electronics is a really good way to implement that. And then finally, there are a lot of technologies like the energy space that are actually driven by metrics like dollar per watt, dollar per kilowatt hour. And in order to get at some of those emerging technologies, really need new manufacturing methods that can allow us to make that in a scalable fashion, but also make it more sustainable. So I'll cover three main topics today. I'm going to begin with our work in liquid metal printed 2D oxides. This work was led by my students Andrew and Sam and Cypher and Simon, and then my former postdoc, Sean, and my current postdoc, Lamin. And we'll move on and we'll discuss essentially energy topics for the second half of the talk. So electronics in the beginning and energy later. So to motivate our discussion of this class of materials and the synthetic method that we've introduced, I want to start with a few fundamental questions. So one of them is, what is it about the disordered materials, amorphous polycrystalline materials, that makes them fundamentally different from an electronic perspective? And is there anything we can do to make disordered materials behave like single crystals? The second question is, can we grow inorganic materials at a lower temperature? Are there fundamental barriers to how we actually synthesize and grow these materials? And then finally, how do we engineer the properties of an ultra-thin semiconductor rather than something that is bulk, like a silicon wafer? Okay, so the focus that we have and the technology that we love the most are based on inorganic metal oxides. Metal oxides are a wide bandgap family of semiconductors, dielectrics, conductors, and wide bandgap is interesting for a few reasons. This is one of the reasons why they're used traditionally in the display industry, is that they can be transparent to visible wavelength light. So we take advantage of that all the time when we're looking at flat panel displays, when we develop electrodes for solar cells. That transparency is an important feature. They're also pretty good. They're really the best thing that isn't silicon. So we can manufacture them in large areas. We can make them have really nearly similar properties when we shrink them down in highly scaled devices. So a lot of really attractive properties. But if we think about flexible and printed electronics, the challenges when it comes to metal oxides are, can we manufacture them at lower temperatures? If you look at some of the applications that these materials have in, for example, energy technologies like solar cells, in flat panel displays, in active interposers, these get more interesting the lower in temperature that we go. So if we can manufacture our materials at temperatures that are compatible with plastics, this is typically a range of 250 degrees or lower, then it means that we can have devices that are flexible or stretchable, that have all these other mechanical functionalities that we couldn't otherwise. Now, if you look back sort of at the last couple of decades, the best way of doing this for flexible and printed electronics was essentially two different options, two different chemistries. One of them used a sol gel chemistry, which was typically a dispersion of metal salts in a solution. And the second was to use nanoparticles. And those two methods, while they can give you relatively good performance, the challenge is that they also require higher temperatures. So higher temperatures translates to essentially a larger embodied energy for whatever device or material you're making. So there's an environmental impact to it. It also means that you cannot use the same range of substrates and you can't have the same functionality integrated, for example, in 3 dimensions with silicon microelectronics. So there's a lot of trade-offs that we make when we use higher temperature materials. So the really interesting processing method or synthetic method that we've been working on, the idea came out of a study published from a group in Australia in 2017 in Science, and they discovered that the native oxide that grows on molten liquid metals can be one thing. It can be highly continuous, so you can essentially transfer it using van der Waals forces to a target substrate. But in doing so, that liquid metal, it's compliant, it's low viscosity, and it essentially preserves the structure of that thin film without destroying the surface oxide. Now, this is surprising for a few reasons. One, that surface oxide grows just a few nanometers thick. So this is a corrosion process that happens just like you would imagine another metal oxidizing, but depending on the metal you use, the kinetics of that process change significantly. So this group, they showed that you could do this on a small scale. We've been working on demonstrating the same method on a much larger scale, at a wafer scale or panel scale for thin film flexible electronics, and applying it to a number of different devices as well. So the fundamental problem that we're getting at in our group is how do we control the electrostatics of these materials at the nanoscale? So controlling the electrostatics means changing the doping of the material, changing the physical thickness of the layers, and being able to stack and influence the interfaces as well. So our version of this liquid metal synthesis uses a roller. We can deform that liquid metal droplet, and depending on the alloys that we design, you're also changing the composition of the surface oxide. So the exciting thing that I think gives us a really a large range of interesting things to study for years to come is that you can change that alloy composition. You can synthesize not just semiconductors and conductors, but also interesting materials that are based on refractory metals like hafnia, for example, or zirconia. So normally you wouldn't imagine that you could put those into a low melting temperature alloy, but it turns out that thermodynamics helps us in this case, that a lot of the refractory metals also have a much larger free energy of oxidation. So it doesn't take a very large percentage in the metal alloy for that composition at the surface to be dominated by the refractory metal. So there's some interesting thermodynamics going on. There's also the kinetic effects that I'll come to later. So our model system for understanding 2D oxides was indium oxide. Indium oxide's essentially one of the most important materials for display electronics, for transparent conductors in energy applications. And indium is also a rather unique metal in that it has a low melting temperature. It's just 157 degrees C. So you can have indium in the molten phase at temperatures that are highly compatible with any plastic we would like to transfer it to. So in this first round of studies, what we did is we found that if we deformed a droplet of indium, that the solid oxide that grows on it would automatically get transferred to whatever surface it's being deformed across by van der Waals. And we discovered, one, that we could form single layers that are just 2 nanometers thick. So why would we want to do that for a material like indium oxide? Well, indium oxide is a little bit peculiar. It displays surface accumulation. It is natively very conductive because a lot of the intrinsic oxygen vacancy defects. So being able to make it thin is potentially useful as a semiconductor because it means we can also electrostatically gate it. So we can put it in structures like a thin film transistor where we could take advantage of that. It also displays an interesting property that some of you might have studied in other courses before, which is quantum confinement. So it is not a 2D material in the traditional sense of a transition metal dichalcogenide where it has a layered structure in its crystal, but it is 2-dimensional in the sense that it displays some quantum confined properties, that it has a density of states that is influenced by its 2-dimensional character. So one example of how that manifests is if you measure the UV vis absorption of this material. As you make it thinner, it shifts the band gap to a higher energy. So this is one of the sort of signs that we typically interpret to mean that we're exhibiting some kind of quantum confinement. And if you look, for example, at the Bohr radius, this is like a homework problem from INJUS 134 or 60. We've essentially thinned it down so it's approximately equal to the Bohr radius in this material. So it's thin enough to exhibit these interesting effects. Well, it has a few other surprises in store for us. One of the things that we didn't expect initially is that this material can also be highly crystalline as deposited. And this disobeys a lot of the intuition that we had for how these materials are synthesized. So for the most part, there are two factors working against crystallinity. You expect the amorphous phase, because it's ultra thin, that the free energy of forming those grains is really favoring the amorphous structure when we get down to the single nanometer thickness. The second reason is that we do this extremely fast. So I didn't mention it when I showed the diagram of the printing process, but it's processed in just about 1.5 to 2 seconds in most cases. So on the millisecond time scale, you're actually regenerating the surface oxide that grows at the liquid air interface. As you crystallize it, you see another interesting feature. If there are any electron microscopists in the room, you might recognize that there are these tiger stripe looking things called moire fringes. The moire fringes indicate that we actually have independent crystallites stacked on top of one another. So this is like a physics problem from high school, if anyone's ever seen it. The period between those two stacked crystallites of their atomic fringes gives us this emergent pattern when we stack the two. So this is very different in so many ways from traditional materials, but at the same time, it behaves a lot like a vacuum process semiconductor. And this is the closest thing. I've worked in a lot of flexible and printed electronic materials before. This is the closest thing I've ever seen to a vacuum process material. That I think one of the properties is that, right, it has this unique grain structure. It's carbon free, right? We didn't introduce any other additives to this material. It's really the reductionist approach to making a semiconductor is you have a metal and you oxidize it. There's nothing else going on for the most part aside from the crystallization. So we're excited as electrical engineers because we can make devices out of this material too. And the properties that it has that are interesting to us are that it can be highly conductive, but at the same time really thin. And this means in a field effect device, like a thin film transistor shown here, that we can turn it on and off. So a perfect thin film transistor, if we're going back to the theory from Ninja 60, would be something that looks essentially like a relay. So it would be completely off, zero current in the off state, and then perfectly on, and it would turn on very abruptly. We get pretty close with this, closer than we ever might have thought before. And that tells us that our material at least has some of the properties one might need if you were going to design flexible circuits, thin film electronics based on this. If we benchmark it against other related materials, for example, from the chemistries that I mentioned earlier, it's approximately an order of magnitude better at the temperature range that we need to put electronics on flexible polymers. Okay, well, there's some other interesting material science going on here. I want to show you some of the other work that my student Sam's been doing recently. Sam's been studying essentially how this two-dimensional form of indium oxide crystallizes. We've noticed a couple of things. One, the degree of crystallinity is important for a number of its properties, electronic and otherwise. Two, the orientation matters. So indium oxide's cubic crystal system, it has essentially the lowest energy facet if it grows along the 111. It also happens to have the best electronic transport properties. So you can move electrons the most efficiently. You can mitigate a lot of the other scattering mechanisms. So we want 111 oriented indium oxide. It turns out the way to grow that is actually if you can deposit it at low temperatures and then crystallize it from the solid phase. So Sam's been developing this process. The idea essentially is that when you first deposit it, you have some nuclei that are already in that preferred orientation. They're interspersed in an amorphous indium oxide, and as you grow them, they start to essentially reach a fully crystalline state that can be highly ordered. And the advantage of that is that you can get better electronic mobility. So this parameter that really determines how good the circuits are that we can make, whether we can switch at high frequencies, all the characteristics that we might need as we go to the system level for thin film electronics. Okay, so to take a step back, what else do we need to know about disordered materials? This is one of the fundamental questions I posed earlier. Well, that property that describes how they differ from a material like silicon is the electronic density of states. So in the sort of traditional solid-state physics theory, we can describe the density of states as all occurring in the conduction band. Then for an electron to be transported, it has to be there in the conduction band. Disordered materials that are polycrystalline, that are amorphous, have a little bit more complex picture. So what in fact happens is that as we add electrons to our material, we're filling up a bunch of traps. And so a good material that looks more single crystalline would be a material that has essentially a lower deep state density in the middle of the gap and a steeper tail state density right near the band edge. And there's a theory known as the multiple trap and release theory that describes this physics. But essentially, if you make materials that are higher in their electron concentration, like the two-dimensional oxides that we're developing here, there's this inherent benefit to being able to avoid the delocalized or avoid the localized transport in these mid-gap trap states and get delocalized transport that looks a lot more like a single crystal semiconductor. There's also some interesting work, I'll point out this in the indium oxide space more recently on highly scaled devices that has shown that, if you do DFT on a very thin slab of indium oxide, it looks significantly different than the bulk. You essentially can shift that fundamental band gap of the indium oxide by about half an EV. So that's actually what we're taking advantage of when we make these materials that we can electrostatically gate. Okay, so because this material is really thin, there are a lot of other interesting things we could do with it. So like other two-dimensional materials, indium oxide is sensitive to its interfaces to a really high degree. Now it's different from some others because it doesn't typically demonstrate surface depletion. It demonstrates surface accumulation instead. It wants to be really conductive even when you make it thin. We can exploit that effect, though, even further if we develop heterostructures where we stack other materials on top of it. And this idea, in some sense, comes from traditional semiconductor devices. There's an effect known as modulation doping in the 3-5 community, where you actually use a wider bandgap material at the interface with the narrow bandgap material to change its electronic properties and to induce some high mobility transport in the channel. Now, the advantage of doping it with a heterostructure compared to doping it extrinsically is that traditionally you can maintain more efficient electronic transport, right? As soon as you introduce dopants into a material that are aliovalent, you typically have some scattering mechanisms that it induces. If you do this with a remote doping approach at the interface, instead you've avoided introducing those scattering centers. But just like I showed you earlier, with this roll-based method, we can still make the grains large. We can mitigate any of the grain boundary scattering also at this larger carrier concentration. So it has a lot of the properties we might want in this case if we're trying to make a transparent electrode. So thin film transistors, one application of oxides. Oxides, because they're transparent, are also really important for a number of sensors. If you want to make, for example, a photodetector or another device, it often has to have a transparent electrode or a window electrode to allow the light in. Solar cell has the same challenge. In our case, by using this heterostructure, we can enhance the conductivity of that indium oxide by a large degree, about 10 to 100x typically. And this effect is so significant because the layer itself is just a few nanometers thick. And you might think of that extent of that electrostatic effect as being approximately the Debye length. The indium oxide in this case is about as thin as its Debye length, at just a few nanometers. Okay, well, as a material scientist, as an experimentalist, how do you understand these properties? Well, you can do measurements like X-ray photoelectron spectroscopy, and XPS can tell you from the perspective of the photoelectrons emitted that there's a shift in the Fermi level. So that's the first sign that sort of corresponds to our hypothesis of the modulation doping. The second thing we might be able to observe is that there's some actually change in the visible range absorption. So it's kind of a funny principle, actually, that if you take this gallium oxide, which is more transparent, but an additional material, and you stack it on top of the indium oxide, the whole thing, the combination becomes more transparent. So you've lowered absorption by shifting the Fermi level in the indium oxide. The other way that we can understand the changes that are induced by the modulation doping are to look at the effect using Hall measurements. Hall allows us to take a magnetic field and quantify the number of electrons that we have in that material, also to quantify the mobility for that transport. It's a little bit different than the measurement of the field effect mobility, but it tells us in this case that the modulation doping does essentially what we thought it did. The interface, whatever Fermi level pinning effect we have, can raise the electron concentration, but at the same time maintain the high mobility, just like you would have in gallium phosphide or gallium nitride or a 3,5 material that functions based on these principles. And if we benchmark it, what we've been able to do in this case with the heterostructure is make a transparent electrode that is flexible, as I showed in the picture before, but also has really high conductivity. So compared to a lot of the competing methods, it has some great advantages for being able to make flexible optoelectronic systems. Okay, well, so we can use heterostructures, we can develop sort of more complex stacks of 2D oxides, but we'd also like to be able to control this degeneracy that we have. So the high electron concentration, it's good for a lot of reasons. It makes a really good conductor, but it makes it more challenging to control some of the non-idealities of thin film electronics. For example, the bias stress stability. So bias stress stability may not mean much to most of you, but it's the reason why we have screensavers. So it's a little bit dated at this point, but if you were to look at a computer from the mid-2000s, right, and it goes to sleep and the screensaver bounces around to try to save your thin film transistors from bias stress. So this is what also limits the lifetime of a lot of display technologies. And what's happening is that the electric field can actually shift the defect distribution in your material. Oxides are vulnerable to this. Amorphous silicon, a lot of the other display materials are also vulnerable to it. But we have a solution, which is that we can control the concentration of the intrinsic oxygen vacancy defects in our material with aliovalent atoms like gallium. So my student Simon's been working on this problem for a while, and it turned out to be a more interesting and more challenging problem than we thought initially. But what he discovered is that gallium and indium, when they're on the surface of the liquid metal, they're in competition to dominate that surface oxide. So there's a lot of literature now on this because of the use of eutectic indium gallium in stretchable electronics. But the short story for what we observed is that you can use essentially a very dilute alloy, so down to the parts per million level, to be able to control this. And you can then form alloys that are still semiconducting rather than purely insulating, but give us the characteristics that we would like. So we can quantify this in a couple ways. One, we can measure the transfer characteristics, the lower intrinsic carrier concentration because of the lower oxygen vacancies gives us the ability to put the on voltage for these devices closer to zero. For a lot of thin film circuits, if you have a display or another sensor, you want to be able to operate with a unipolar power supply or unipolar circuits. Having a turn on voltage near zero gives us the ability to do that. The other thing we're able to do is actually adjust the density of states. So the gallium is essentially lowering the density of states, particularly in the mid gap, by reducing the Gaussian distribution of the oxygen vacancies. And then the final peculiar thing that Simon found is that it's actually still crystalline. So gallium, it has a different ionic radius. A lot of people before have observed that the gallium tends to actually amorphize the material. In our case, it remains in the cubic phase, even up to 8 or 9% gallium doping. Okay, so we have doping we can use to control 2D oxides. We have heterostructures. The third mechanism that we've been exploring more recently is actually the kinetics of that process. So how do we control the growth and the thickness of that 2D oxide? I said before that we could print it, but if we can print it, that means we also have control over the dynamics of this liquid metal meniscus. And if we change the speed at which we deform the meniscus, what we're also doing indirectly is controlling how thick that oxide is going to grow before we transfer it to the substrate. Now, the process that governs this is Cabrera-Mott oxidation. It's the same process you might observe in the clean room. If Phil has mentioned this in class before, it's what happens to a silicon wafer when you leave it out and it grows that native oxide. Metal oxides form a little bit thicker layer, typically 2 to 3 nanometers thick, but it happens in the millisecond or even microsecond timescale. So if we're going to control it, we have to print fast, and that's the mechanism that we've been using. There are a few unexpected things. One, it tends to grow the same thickness everywhere. Doesn't really matter if we do it on a large scale, tens or hundreds of square centimeters, or a really small scale. So it tells us that it's really the kinetics of that Cabrera-Mott process that are governing everything. We can control it with temperature. As you might expect, it's thermally activated, so we're relying essentially on a competition between the diffusion of the oxygen anions across that barrier. So they have to burrow or they have to diffuse their way through the metal oxide film. The reason it's fast at the initial growth stages is actually because of the electric field. So Cabrera and Mott discovered this about 80 years ago, and they were surprisingly right. Like about 90% of the features of this process they predicted based on the thermodynamics about 80 years ago. So why does that matter to us? Well, I mentioned earlier that if we're going to dope our material, it gives us some additional control over the electrostatics. But at the same time, we still need control over the thickness, right? If we want to shift the threshold voltage, if we want to design electronics based on this technology, then we need to have some control over that precise thickness. And ideally, we'd be able to drive down that thickness even further. So at the smallest scale, when we introduce a dopant like antimony, we can control it down to the 1 to 2 nanometer scale. Now, antimony is an interesting choice. It turns out that unlike a lot of other dopants like tin and gallium, antimony can actually enhance the mobility and enhance the effective mass in the indium oxide. It has a little bit different influence on the band structure. So we've demonstrated this recently in my student Sam's work, and we've noticed that you essentially have two things. One, you're able to introduce the dopant to improve the material, but at the same time, you're able to still gate it because you can make it even thinner and allow it to essentially be fully depleted by the gate voltage. Okay. So I want to say a few more things about oxides, and then we're going to move on to the next section of my talk on energy devices. One of the other interesting aspects of that kinetic control is that we can start to use materials that we can also print at lower temperatures. So one of the eutectics that we've been working on is a mixture of indium and tin. And indium and tin, if you're familiar with it from low temperature solders, melts at about 117 or 120 C. So you can bring the temperature down even lower. You can put it on a range of different plastic substrates. The surprising thing, though, is that even with this low temperature printing, we can get morphologies that can be highly crystalline, that can have relatively large grains. The large grain aspect is something important to us because in a lot of cases in these materials, one of the main dominant scattering mechanisms is when an electron is scattered from the grain boundary. So if you have a larger grain material, in total you have a smaller effect from that grain boundary scattering. The other thing that is a really interesting feature of this that we haven't really had a chance to dig into yet is that having a mixed phase, so some amorphous metal oxide that essentially separates those grains, can give you better strain tolerance. We care about strain tolerance because it is still an inorganic ceramic material, right? It's not something like a polymer that's essentially designed from the atomic scale to have greater strain tolerance, but it can be good enough essentially to sustain bending at the single millimeter scale. So something that is nearly foldable if you want to think of the mechanics of it. So my student Cypher was developing some different applications for this two-dimensional indium tin oxide, and one of the applications that stood out to us was the ability to make bioelectrodes that were also transparent. It's an idea that some of my colleagues have already exploited in other kinds of biomedical devices. But indium tin oxide, it turns out, has pretty impressive properties as an interface to the skin. It can have a relatively low contact impedance. If we're trying to make an interface, for example, to take electrocardiography measurements, then that contact impedance is a good sign for us that we can get high SNR. It also has a relatively good resilience under abrasion. So for any wearable device, we're always concerned about the reliability. And so a material like a ceramic that has pretty good resistance to being scratched is also an ideal material for this case. But what's really interesting and what my student Cypher showed is that there's a side benefit, which is that if you're doing it with the transparent electrode, you can simultaneously collect multiple measurements, in this case, from the same measurement site. So you could have a wearable device, which is highly miniaturized to begin with, that collects a signal like pulse plethysmography at the same site as the ECG. So we're working now on essentially trying to take this method and use the fact that we have those two correlated signals to do some signal processing to make it more robust to things like motion artifact that are a challenge for wearables. And I think there's some other interesting directions that could emerge as well. Okay, so with that, I'll transition to the second part of my talk. I want to say a little bit more about energy in this section of my talk and talk specifically about how we're using additive manufacturing technologies for designing energy devices and controlling the mass transport. This work was led by my postdoc Anand, my students N.A., Cypher, and Julia. Okay, so I want to motivate it with a few fundamental questions like we did earlier. And the first is, do 3D architectures make sense for functional materials? There's a lot of work in the past on mechanics, and if Rebecca's around, Rebecca and her group have done a lot of interesting work to show that there are mechanical advantages to 3D microarchitectures. There's less work to demonstrate that there's a need or an interesting application of 3D printing in functional materials for electronic applications and electrochemical applications. So I'm going to come back to that in a moment. The other sort of fundamental question we want to answer is whether or not the three-dimensional structure can program some electrical and electrochemical properties. And I'm going to show you that it can, in fact. And then finally, what tools do we have to design three-dimensional electronic materials? You're not going to use Cadence. Cadence is designed for integrated circuits. So we need other design tools that allow us to predict the properties in 3 dimensions. Okay, so additive manufacturing technologies, they're interesting for a number of reasons as a prototyping technology, but I think there are also some interesting applications in situations where we need complex geometries. Now, some devices like batteries have a relatively simple geometry. You have a stack up of layers, they might be rolled together. But if we want to move energy devices, for example, onto the microscale, like you wanted to integrate a battery directly with an integrated circuit at the smallest dimensions, the three-dimensional geometries become more complex. If you want to integrate a supercapacitor, for example, in a very small system on chip, you have the same challenge. And in the last case, if you want to develop materials, for example, for electrocatalysts and hydrogen production, you have now another set of geometrical challenges that require essentially complex assembly and design to achieve some mass transport limitations or mitigate mass transport limitations. So I'm going to focus for the most part on our applications for electrochemical devices here. I think there's a lot of interesting other devices that you could pursue. And the motivating factor for us is the need for catalysts that can support lower cost hydrogen generation. So the growing hydrogen economy depends essentially on having new materials that can go beyond the platinum group metals that have been used in the past. Most of our current electrocatalytic or electrolytic hydrogen production depends on materials like platinum and iridium oxide that are highly scarce. And so if we're ever going to get closer to the goal that has been set by agencies such as the Department of Energy for $1 per kilogram of hydrogen, we have to think more broadly. We have to think about earth-abundant materials. I think additive manufacturing is a great way to make some of those earth-abundant materials perform high enough that they could replace those precious metals. So our starting point in this area was trying to understand how we can take 3D printed polymers. We know really well, based on additive manufacturing technologies that have been scaled at this point, how to 3D print polymers. We can use photopolymers, we can design their chemistry, we can design their mechanical properties. The only problem is that they're not conductive. So what tools do we have to actually make that three-dimensional structure also conductive or semiconducting? Well, we could coat it with the material. I'll show how we do that in a moment. Or we could directly convert it to a conductive phase. So it turns out if you heat a polymer, if you heat it in air, it'll burn up and disintegrate. If you heat it in nitrogen, you can essentially take many different polymers and you can carbonize them or form a conductive graphitic phase. So we're able to do this, for example, for a 3D printed polymer that we make by stereolithography. You can maintain that structure and you can actually enhance the resolution as well. So there's the synergy between the post-processing methods that actually make it higher resolution, give you control over the geometry, and control over the electrical and electrochemical properties. But some of the other challenges are, right, what 3D structure do we even want in the first place? I think that's an interesting question, and not one that there was an obvious answer to when we started working on this. There are a lot of structures that were good mechanically, but we have no idea what their electrical properties are. But there's a good approach to this, which is informed by plenty of work that electrical engineers have done in the past. It looks a lot like the way that we build models for SPICE and other circuit simulator tools, which is using essentially a graph theory approach, or approaches informed by graph theory, where we can model a resistive network. And if we can do that, if we can represent every one of the components or the elements in our three-dimensional structure as a resistor, then we can compute, for example, what the conductivity, what the resistance is between any two points in that structure. We can predict some of the electrochemical properties that we observe. So the approach that my student Julia developed was based on essentially that assumption, and there's some very straightforward ways to do this, even in tools like MATLAB. It is really a surprising, few number of lines of code to actually calculate this, which is good because it's also typically more computationally efficient. So we can explore a bigger design space and we can say, well, what three-dimensional structure do we want? If we want to make it conductive, there's going to be this trade-off between the mass, the surface area, all these other properties that are important for energy devices and electrodes. And so what we discovered that there were a few lattices in particular that did really well. They usually weren't the same lattices or the same three-dimensional structures that were mechanically strong. So the mechanically strong lattices were the ones that essentially had cross-bracing, had some additional elements in the opposite direction. The 3D structures that were the most conductive electrically per mass were actually the ones that were pretty simple. So a BCC lattice that's essentially a bunch of diagonal crosses, or a cubic lattice, a simple cubic lattice, were the best because they had the most elements in the direction of the current flow. So there are a few different ways we could exploit this. The first project that we worked on, my student Cypher and Julia both developed, was using this approach of coding three-dimensional lattices as a porous architecture to be able to do sensing. So gas sensing, anemometry, there are a number of methods that require essentially some interface between an electronic material and the air or some kind of medium. The advantage here is that we have complete control now over the mass transport. And this is where we started thinking, well, if we could design the structure, its electrical properties, we could also design it to have some optimal response, in this case, to different stimuli. It could be chemical or mechanical. We won't have a lot of time to get into this, but I think it was really the seed for us to think about how we designed the rest of these electrodes for energy devices as well. And I want to move to talk a little bit about electrocatalysis, because electrocatalysis is this fascinating problem that essentially exploits the 3D geometry. And the way that we're doing that is we're changing from a bulk processing method. So batteries, catalysts, a lot of materials traditionally, they're made by casting a slurry. And so that slurry essentially has a random set of sizes of those particles, a random distribution. It's really good for simplicity's sake, right? We can synthesize that material more simply. But the challenge is that it's not actually very good for controlling the mass transport. And there's some interesting work in the catalyst community more recently that if we want to get high performance at high current density, then we have to think really carefully about how we transport electrolyte and how we transport bubbles. So that's really the challenge that we've been trying to address with this integrated approach. So the chemistry that we've been working with is essentially a variant of infusion additive manufacturing, which is quite similar to something you might have seen in the Jones seminar talks last year from Rebecca Gallivan. Our version of infusion additive manufacturing doesn't use a hydrogel. In this case, we started with an organogel or a polymer that was 3D printed. We were able to control the infusion in this case, rather than going fully into the material to create a 3D printed metal. In this case, we're forming a core shell structure that has some active material. This is actually ideally what we want for the catalyst, right? Any material that we introduce, we want it to be in contact with the electrolyte, because that's where it's actually doing the chemistry we want to happen. In the core of the lattice instead, at each beam element, we have that graphitic carbon that we developed earlier. So what we discovered is that this structure, well, the first feature that we care about is that it can have some essentially mesoscale structure. It can have some pores that could give us the electrolyte diffusion and the bubble evolution, but it also gives us some means of controlling the nanoscale structure at the surface. So for most electrochemical devices, we want high surface area. We can get that in two ways. One of them is by having the mesoscale structure, and the second is by changing the micro or nanoscale structure at the surface. What we end up developing actually after it's been converted at a high temperature is some mixed phase. The mixed phase in this case often has the most interesting electrocatalytic properties. So it's a mixture of metal and metal oxide at the nanoscale, as well as the carbon to be able to essentially extract the current or inject the current from our device. But at the same time, we're controlling essentially this high surface area form of the cobalt oxide or copper oxide. We were focusing on both HER and OER, so these are two different reactions that we could perform electrocatalytically. And if you haven't seen a plot like this, what we're trying to describe essentially is how much overpotential or how much additional voltage we have to apply to be able to generate a large enough current. The level of the current generated essentially corresponds to how much oxygen we're evolving or how much hydrogen we're evolving, depending on the reaction that we're running. And the interesting advantages, one, are that the three-dimensional structure, it has more accessible surface area. It doesn't get blocked by the bubbles. So it has higher activity than the same material in the form of a powder. The other thing is that the activity of the catalyst depends on the three-dimensional structure. I don't know if we expected to see this when we started out, but it was really an interesting result that showed that the way the bubble moves is really important. If the bubble gets stuck in lattices that have a more complex internal unit cell like the octet, then you essentially can't allow the electrolyte to access the rest of the material and complete the reaction. The cobalt oxide are perhaps the most high-performing materials that we've developed by this approach. And if you benchmark it against the commercial standard for these metal oxides is typically a metal foam. Well, that metal foam is a random porous architecture. This is an ordered porous architecture, so we have control now of what the bubble evolution will look like. So Cypher developed a really nice experiment for this. We have a little bit of computational work from one of my former undergraduates, Vibhuv, who showed in these illustrations that essentially the cubic lattice allows the bubbles to squeeze through so that they can evolve in an efficient manner, whereas when you have a lattice like the BCC or the octet, they tend to get trapped at all of those angled facets in the material. But if you track the bubble with high-speed microscopy, what you find is that the bubbles move at different speeds. So for one thing, the bubble speed depends on essentially the size of the bubble. But for another thing, it depends on whether the buoyant force is aligned with the channels that we have. Now, the cubic lattice is nice because the buoyant force is now perfectly aligned with the channel throughout the whole slab of the material. So we think this is like an interesting property that you couldn't get from a random material. It simply won't ever be the case that it will be aligned with the pore structure. So I don't know if the video is going to play, but this is essentially a video showing the bubble evolution from one of the microscale lattices as it's being run through the electrocatalysis reaction. And one of the benefits of having this three-dimensional structure is that it can also be more stable. So instead of having to worry about the bubbles occluding or blocking the active sites, in the case of the three-dimensional lattice, it can be much more constant in its current density and can extend the lifetime of a material like a transition metal oxide that is otherwise limited in its operational stability. Okay, well, good. So I want to move on to talk about one more energy topic before we run out of time, and that's the topic of flexographic printed solar cells. So to bring this full circle, right, we're thinking about scalable manufacturing. We're thinking about the high performance materials that are useful for flexible and printed electronics. So we have on the one hand, hydrogen generation and energy conversion. And then the last vignette here, we have energy technologies like solar cells that benefit essentially from the scalable and the high throughput manufacturing. And we have a couple examples of solar cells, or at least the solar absorber before the cell is finished, one of them with the Dartmouth Pine logo. So to give a brief introduction to thin film solar, there's essentially a competition between all the different materials and device technologies that one might use to produce solar energy. Solar energy is interesting, at least because it's this huge potential resource, right? We don't leverage it to any real extent in the United States or globally like we might, because there's really, like, if you compare it to power from other sources, geothermal, wind, right, it really is exponentially larger, orders of magnitude larger. But the challenge is, can we make materials at low cost, right? That's what drives the development of solar energy. That's what drives the deployment of solar energy. And one of the emerging candidates that has advanced really rapidly, this is a plot that's shown very often at conferences and in other talks for perovskites. And what it tracks is the photovoltaic conversion efficiency, or PCE, for different solar technologies. And at one point, people thought, well, if we can make a flexible device, we don't really care how efficient it is. It's turned out that because of the balance of systems costs and a lot of the complexity of permitting, that we still need a really efficient device. We just also want it to be cheap if it's going to take over the incumbent technology like silicon. Perovskites more recently have hit a single junction efficiency of 27%. So they're essentially at parity with silicon and have been for several years. So if that's the case, I guess I don't need to say any more, right? It's already been done. But the truth is that there are a lot of more significant technological challenges of chemistry, of material science to solve before this thing is going to be on everyone's rooftop. And it comes down to how we protect this ABX3, the methyl ammonium lead iodide structure that I've shown up here. It turns out that because the methyl ammonium lead iodide has a couple things going on. One, it has this organic cation. The organic cation itself has a relatively low melting temperature and boiling point, so it's volatile. And as the solar cell operates, it's exposed right to a lot of heat. It's exposed to UV. It's exposed potentially to moisture depending on the encapsulation technology that we use. So whatever solar absorber we're going to use has to be resilient to all of those different stimuli. The other challenges that have to be overcome, or if we're going to put it in the field, right, and develop a fielded module, is actually integrating multiple cells in series. So we talked about this in just 60 just a couple of weeks ago, but when you're developing a solar panel or a solar module, you have to string all the cells together. You lower the resistive losses that you have at the interfaces between each one of those cells and the rest of the module by doing that. But the challenge is for a material like perovskite or organic photovoltaics, anything where you're making a monolithic module, the challenge is how you connect them together. It's not as simple as putting a wire between the two like you would for a silicon solar cell. But if we can do all of these, the promise is that the manufacturing cost for a material like this could be very low. It's earth abundant. We can make it potentially with technologies that have a really low capital expenditure. And that's essentially the key piece. So the technology that is the most interesting for being really low capex is something like we use in the graphic arts. There we go. So this is a offset printing press, which you might find if you went to any location that prints newspapers. It's pretty similar in theory. It's not precisely equivalent to a flexographic printing operation. But what we're doing in our lab is essentially borrowing a lot of the techniques that were developed over 200 years in the printing industry. And people have gotten really good at printing. It goes back centuries in places like Germany. And then there are other cultures, like Japan is also an expert at printing, it turns out, because the characters, particularly in texts and other things, have to be essentially produced at a really high resolution. So we're borrowing from all the knowledge that was already out there in the graphic arts field. And what we're trying to do is push it significantly further in that we can control it like we would a semiconductor technology. So if you went in the clean room and you wanted to make a solar cell, of course you need good control over how thick all of the materials are. You need to have good control over their electronic properties. But we're doing it now with a method that is very different, right? We're taking an ink. That ink is some solution of metal salts and that organic cation. We're controlling its drying and its crystallization. There's a lot of intermediate steps that it has to go through. But in this case, the advantage of our method is that, one, it's very fast. We can do it over large areas, and we can decouple some of the physics of the printing itself and the processing that happens afterward to form the crystalline phase that we want. Well, I think we skipped Julia's video. So Julia has a video. It's a slow-mo video that she captured with her iPhone, so I appreciate that they had that feature when she did this work. And if we had the sound, you would hear it slamming into the back. So this happens at a meter per second. A meter per second is really fast, right? It's like hard to really conceptualize until you see it happen. That's the whole operation. Like, that's the printing of the solar absorber. So it happens quickly, and that sort of is illustrative of the fact that if you have a high throughput manufacturing method, now you really could make, not just square meters of this stuff, but square kilometers. You could cover the Dartmouth green if you wished. So what are the other challenges and what are the opportunities if we have a method like flexography? Well, printing methods are good at printing. They're good at patterning things. And that's something that you don't have with a lot of the competing methods. So if you have vacuum deposition, you typically have to combine the deposition with some lithography or patterning. The problem with perovskites is that they basically dissolve in everything. Like, there's really only 2 solvents that they don't dissolve in. So if you tried to take them in the clean room, you can't really pattern them with lithography. But I mentioned earlier that if you're going to make a module, we have to do exactly that. So the way this has been handled in industry is typically to use a method like laser scribing. So you blast it and you ablate it away. But again, that perovskite material, it's highly sensitive to heat. It's highly sensitive to other factors that destroy it and seed degradation. So one of the advantages of being able to print it in this case is you can get low lineage roughness. You can form micron scale features for linking the different cells together in that module. And you can do so without causing any additional degradation pathways. Okay, well, what are the other interesting physics that happen when you try to print a solar material? You're trying to make a film that's just half a micron thick, right? So it's not something we typically do with fluids. The fluid phenomena that we're fighting are essentially the tendency for films, when you pull them apart, to form this Safman-Taylor defect. So if you have 2 different fluids, air and the ink in this case, with vastly different viscosities, there's this phenomenon that you can observe, for example, if you peel 2 sheets apart, where they form these viscous fingers. And this viscous fingers, it turns out, are the biggest challenge for us in printing solar cells, to be able to make that uniform thickness of the solar absorber. What's helping us in this case is actually the surface tension. So fluids, they like to minimize their surface energy. They like to minimize the surface area. So what's happening during this leveling process is the surface tension is pulling that variation in the thickness flat. And what we find is that there's actually this deeper correlation also between the fluid film thickness and then the optoelectronic properties. So maybe this was obvious, but it certainly was a surprise to us when we found these images, that the photoluminescence and the other optoelectronic properties would essentially give us the same kind of image that you'd get from variations in the thickness. So it's telling us that if you want to make good solar cells, you really have to print it perfectly. You have to go essentially to a length scale or a uniformity scale that you could never achieve before with typical graphic arts printing. And that's essentially at the single nanometer scale for the variation. Now, the reason we care about that for perovskites in particular is that there's a pretty narrow process window. So we'd like to form a dense grain morphology that doesn't essentially allow any pinholes where you could have shunt current flowing. This is how you make a really efficient solar cell, is preventing any shunts that add to the dark current but don't give you photocurrent. You can map that essentially with an aerial photoluminescence. And the message from all this really is that if you want to make a good solar cell, you have to print a really uniform film. If you do that properly, you can make devices that have an efficiency that's on the order of commercial silicon. So if you went out and bought a commercial silicon solar panel right now, you would get something about 20 to 22%, depending on how much money you spend. The perovskites that we print in our lab are about 18 to 20%, with champion efficiencies on the order of 21 now. But how do you go further? If you're going to go from the lab scale to something that's much larger, right? Square meters, you have to think about accelerating our development from the small scale to something that's larger and more complex. And the tool that we've been using in my group that Masha and Yana have been leading is essentially an applied machine learning technique. So it's a sequential learning method that uses Bayesian optimization to take all of this information we have now, right? We have the correlation, or we have the data and its dependencies on the printing physics. We have the dependencies on the ink chemistry and everything else, the mechanics of the contact pressure. And the Bayesian optimization gives us something that you really can't wrap your head around as an experimentalist. As an experimentalist, we're really good at mapping things out along single variables. But it turns out if you want to explore a 7-dimensional space, that's a really inefficient way of doing it. So Bayesian optimization, on the other hand, can allow us to sample that space, create this Bayesian process model, and then march forward and improve the efficiency of the solar cell in this case. So to wrap things up, I think I want to save a little bit of time for questions. So to wrap things up, I think some of the most interesting questions we're now asking as a result of this are, can you push machine learning and related methods like artificial intelligence further? Can you go beyond just the exploration of new materials? Can you develop materials that are co-designed with devices or circuits or the process itself? Can it also inform the fabrication, right? Give us new intuition for what the fundamental challenges are, right? If you have 7 variables or 8 variable space, can it tell you which ones are the most important, for example, and hone in on what the most significant challenges are from different aspects in the chemistry or the mechanics? And then finally, can it get us towards energy technologies that are ready to scale? I hope the answer is yes in that regard. So with that, I'll wrap up and open it up for questions and, acknowledge my group again, of course. Thank you.